I'm a dissident prophet. You'd see me in such fine quality, epic physics education videos such as The Forces That Be and Gravitation. Please don't hurt me, yo. Okay, so in chapter 7, we've been talking about circular motion. We are bypassing torque at this point, and we're looking at our objectives here. We're going to be looking at the helio and geocentric theories, models of our solar system. We're going to look at Kepler's 3 laws of planetary motion and understand Newton's discovery of the law of universal gravitation. You should be able to calculate it and explain the device that was used for this. So with this, let's go. So seriously, old school ideas. The geocentric theory is that the Earth is the center of the universe. The sun and the planets revolve around the Earth. Now, who used it? Well, the Greek philosopher Aristotle. Mesopotamian priests. They used that to deceive their king with astrology. Okay? Because astrology is based on movement of stars and planets and all that. But that's the geocentric theory. Then, later on, there was something called the heliocentric theory, where the sun is at the center of the universe. Now, who believed it? Well, there was Aristarchus of Samos, who was a Greek. We also had Claudius Ptolemaeus, where planets travel in circles. Well, now we're getting a little bit closer to what we understand today. We know that the geocentric theory wasn't going to work. The Earth is not the center of the universe. Okay. We also have the heliocentric theory. We looked at it. We talked about Aristarchus and Ptolemaeus, but Nicholas Copernicus was a Polish dude who believed that the planets did orbit the sun in circular orbits. Now, these guys were mentioning that the planets would go around, including the Earth, around the sun in a perfect circle. Well, that's not entirely correct. But they were better than the geocentric theory. So in 1543, we had Nicholas Copernicus. Okay? And he came up with the model of the sun-centered system where the planets moved around it. Okay? So that's how he came up with it. Now, later on, we had in 1560, so we jumped from 1543, almost a little over 100 years later, we have Tycho Brahe. I call him a baller because this is a guy, when he was a kid, he saw a solar eclipse and he wanted to become an astronomer. He never used telescopes as he designed and built his own instruments. Baller. That's all I'm saying. He used his own gear, developed his own gear, came up with some explanations. He agreed about the idea that the planets were going around the sun in a circular motion, but that wasn't explaining, well, what about the moon? How was that going around it? Well, that the moon was going around the Earth while the Earth was going around the sun. So that was kind of like the best explanation that he could come up with at that point. We move on in history. We have Johannes Kepler, one of Brahe's assistants, and he came up with the laws of planetary motion. And the idea is, number one, planets move in an elliptical orbit with the sun as one of the foci. So this is it right here. Here's an illustration. So instead of being that perfect circle, which was our heliocentric theory, now it's been modified. Instead of being a perfect circle, now it's more of an ellipse. Think of it like a squashed circle. So the sun, there's 2 center points, if you will, here. 2 points where the planet is revolving around. One is the sun. The other is some point in space there. And what happens is, as the planet is the closest to the sun, that's when it's moving the fastest. When it is the furthest away from the sun, that's when, or aphelion, that is when it is its slowest. So in the winter time, we are at perhelion. We are at perhelion around December 21st, 22nd, and then we're at that aphelion furthest away from the sun around June 21st. Okay, so our winter solstice and our summer solstice. Now, Kepler's law of planetary motion number 2 is saying, as the planet orbits the sun, it moves in such a way that a line drawn from the sun to the planet sweeps out equal areas in equal time intervals. Lots of words, we need a picture. And here's the picture. So here's our planet going around the sun in its elliptical path. We're going to use the sun here. So the planet from point 1 goes to point 2 in a certain time. Now, there is an area that is swept out. This kind of looks like a piece of pie, if you will. That's area 1. And then here on the other side, period 3, point 3 to point 4. Okay, that's area 2, and that takes the same amount of time compared to here, going to here. Now, if you notice, the area 1 and area 2 are meant to be the same. That's the weird part, because we're seeing this happening where this area and this area will be equal to each other. Even though this is going from point 1 to point 2 in, let's say, 25 days, if this is going from point 3 to point 4 in 25 days, it's moving a little bit slower. That's true. It is further from the sun, but the area swept out is the same. The third law of planetary motion, and this is a mind-boggler, the ratio of the average distance from the sun cubed, so that's our r cubed here, to the period squared. Now wait, what's the period? The time it takes to go around one full revolution. So in the case of the Earth, our 365 and 1/4 days, one full year, okay? So the ratio of the average distance from the sun cubed, that's our r here, to the period squared, that's our time, is the same constant value for all the planets. So this formula, t squared, our period, our time it takes to go around the sun, square that, divided by the average distance from the sun to the planet cubed, is equal to some constant k, a planetary constant. Now, here's the kicker. This is true for all the planets of the solar system. Mind blown. It's true for all the planets in the solar system. Psalm 19:1 says, "The heavens declare the glory of God, the skies display his craftsmanship." It's not an accident. It's not. There's a design, and there's a consistency in that design. Somebody had the brains to put all this together. In other words, guys, it's not about me, and it's not about you. It's about him. All right, let's keep moving. So, now we got to talk about the law of universal gravitation. We've looked at the heliocentric, geocentric ideas of the solar system. We looked at Kepler's laws of planetary motion, and now we're looking at Newton and how he began to study planetary motion. There is something called a gravitational force, and that's the force of attraction between two objects that's proportional to their masses. Okay, there's also a relationship to how far apart from each other they are. The further they are apart, the less gravitational attraction there is. But that's also depending on how massive the object is. So every object out there puts out a gravitational force. Even the flea that would be on a dog in the street puts out a gravitational force on the dog. The dog puts a gravitational force on the flea. Yeah, you're saying you're kidding. No, I'm not. Because remember, any object has a mass to it. When an object has mass, that means gravity is being put out. Now, yeah, it's not going to be much, but it's there. Just as I'm putting gravity to this camera. Yeah. Got the power of gravity working for me. Yeah. All right. So, for Newton's law of gravitation, a gravitational force is equal to the gravitation constant times the masses of our objects divided by r squared, or where r is the center to center distance, center to center of each object of the two objects themselves. So wait, if there's this gravitational constant, how did they come up with it? Well, there's this other guy in 1798 named Henry Cavendish. Henry Cavendish decided to develop a device to measure this gravitational attraction. Now, it took nearly 75 years to calculate the accurate G constant. Now, he never did calculate the actual value of G. He could have. Now, Cavendish was involved in other experiments too, so don't get any wrong ideas. He just measured, he had a device, he developed a device to measure this gravitational attraction. So this is it. It's a torsion balance. You have two objects of a bigger mass. Now, they're the same objects, so same size, okay? And they're same distance apart. Here you have a bar attached to a wire, and then you have two smaller objects, same size, same mass. Now the idea was that the radius between the two objects, center to center, okay, there's your radius, then how did we figure out the G? They looked at the twist on the wire, the torque on the wire, the twist on the wire. The more of a twist, that meant there had to be more gravity involved. And with that, they were able to figure out what is the gravitation constant. So this is our formula here. Okay? So with that here, guys, we can look at the gravitational attraction between a 20 kilogram bowling ball and a marble. That's our force of gravitational attraction. 48 times 10 to the minus 10, and they're separated center to center by 30 centimeters. So, given that, okay, given all this information here, and our gravitation constant is this, what is the mass of the marble? Okay? So that is literally the end of chapter 7, but let's see if we can go. Do I have the time to figure out the gravitation mass? Actually, I do. I have to check on my timing for my thing. I erased it. Okay, well, let's go back and let's work that through here. So with this, ladies and gentlemen, let's start looking at our values. So our gravitational force here, and we're going to work with these numbers, 1.48 e to the minus 9th. Instead of saying times 10 to the minus 9th, we're saying e to the minus 9th, just like they do on those TI-85s, is equal to, well, 6.67 e to the minus 11 multiplied by our mass, 20 kilograms, multiplied by x, over our r, which is 0.3 meters. Okay, now I'm going to double check, make sure I got my formula right. R squared. Okay. So that has to be squared. So this has to be squared. Okay? So with that, ladies and gentlemen, we can now go ahead and do some multiplication. And then we can figure out the mass of a marble, which is not going to be a whole lot. All right. That's basically it for this chapter. All right. At this point, I am now going to sign off.